The F-16 Fighting Falcon, the most successful fighter jet ever built, was designed to crash, and that decision changed military aviation forever. In the skies over Vietnam, the United States Air Force faced a clear systemic crisis. The primary American fighter, the McDonnell F-4 Phantom, was a heavy, missile-reliant machine built on the assumption that modern air combat would be fought with long-range radars at extreme speeds. But North Vietnamese pilots flying smaller, highly agile Soviet-built MiG-15 and MiG-21 fighters forced a different reality. In close quarters, dogfights, the lumbering Phantoms were repeatedly outturned, unable to preserve their energy after sharp maneuvers. Colonel John Boyd, a veteran who flew 22 combat missions in the F-86 Sabre during the Korean War, studied these tactical failures. Working at Eglin Air Force Base with mathematician Thomas Christie, Boyd developed Energy-Maneuverability Theory. This mathematical system quantified an aircraft's performance as a function of specific energy and thrust to weight ratio. The theory proved that a lighter, high-thrust aircraft with low wing loading would dominate the combat arena by maintaining its energy state during tight turns. Boyd proved this concept through action. As an instructor at the Fighter Weapons School, he issued a standing $40 wager. He would start a mock dogfight from a position of total disadvantage at 30,000 feet and reverse the situation to secure a simulated kill in under 40 seconds. He never lost. It proved that the pilot who manages energy rather than firepower controls the sky. Pentagon Systems analyst Pierre Sprey, collaborating with Boyd, formed an underground network of reformers known as the Lightweight Fighter Mafia. This group bypassed traditional Air Force acquisition channels to advocate for an austere, highly agile visual fighter. They rejected the prevailing military trend toward heavy, expensive multi-role aircraft, arguing instead for a platform optimized strictly for air-to-air combat. At General Dynamics, project engineer Harry Hilliker translated this performance-driven philosophy into a concrete aerodynamic design. To achieve the extreme turn rates demanded by Boyd's theory, Hilliker took a calculated risk. He designed an unstable airplane. Conventional aircraft placed the center of gravity ahead of the center of lift to ensure natural stability. Hilliker did the exact opposite, moving the center of gravity aft of the center of lift. This relaxed static stability meant the airframe would naturally want to pitch up and slice through turns, but it also made the aircraft aerodynamically uncontrollable by a human pilot. In 1974, this radical design faced its ultimate test at Edwards Air Force Base, California. Under the Lightweight Fighter program, the General Dynamics YF-16 entered a head-to-head evaluation against Northrop's twin-engine YF-17. Across 268 test flights, the YF-16 demonstrated superior transient maneuverability and lower operating costs. On January 13, 1975, the Air Force officially selected the YF-16, turning a controversial engineering theory into the future backbone of global air power. In 1971, former Apollo 11 commander Neil Armstrong pushed to transfer digital spaceflight guidance systems directly into atmospheric aircraft. NASA acquired a retired 1958 Navy F-8C Crusader, completely stripped out its physical-mechanical control linkages, and installed an Apollo guidance computer to drive the control surfaces. On May 25, 1972, research pilot Gary Creer took off in this modified testbed. This was the first time an aircraft flew with no physical backup system, relying entirely on digital electrical signals to coordinate flight. Over 13 years and 210 flights, this research program validated the exact multi-channel digital architecture, redundant sensors, and high-frequency control loops required to keep an unstable airframe in the air. This experimental work proved that digital control systems were reliable under extreme flight loads. The fundamental computing challenge was solved in flight years before the YF-16 ever had to rely on it. In conventional aircraft design, safety dictates positive static stability. If a gust of wind bumps the nose up, aerodynamic forces automatically push it back down. The plane is self-correcting. Relaxed static stability alters this fundamental rule. By shifting the center of gravity rearward, engineers built an airplane that is intentionally less self-correcting. When the nose pitches up, the aerodynamic forces push it further up, causing it to diverge immediately. This inherent instability is precisely what makes the aircraft highly responsive. Because the airframe does not fight against its own trim, it can pitch and roll with minimal aerodynamic resistance. To keep this unstable design from tearing itself apart in mid-air, the flight control computer must intervene continuously. The system processes pilot inputs, instrument readings, and structural loads, sending adjustments to the control surfaces 40 times every second. Engineers often describe this process as balancing a pencil on a fingertip at Mach 2 while pulling 9 Gs. The extreme extension of this engineering logic appeared in the F-117 Nighthawk. To scatter radar waves, designers covered the aircraft in flat, angled panels. This shape destroyed conventional aerodynamics, leaving the F-117 unstable in pitch, roll, and yaw. Skunkworks engineers joked that the blocky aircraft looked like the box it should have shipped in. Yet, digital flight computers managed all three axes of instability, translating pilot intent into stable flight. This validated the core philosophy of the lightweight fighter mafia. An airplane already inclined to change direction reacts faster than one that must be forced into a turn. By making the airplane aerodynamically worse at staying stable, engineers made it infinitely better at combat. On January 20th, 1974, at Edwards Air Force Base, the physical danger of deliberate instability nearly destroyed the Sol prototype. During a high-speed taxi run, the YF-16 began violent roll oscillations, its left wingtip and tailplane scraping the tarmac. Test pilot Phil Ustricker faced a split-second choice: force the bucking aircraft back down and risk disintegration, or throttle up into the sky. He chose to fly. Ustricker kept the unstable airframe aloft for 6 tense minutes, landing safely after managing a miswired exhaust nozzle circuit. This unscheduled liftoff became known as Flight Zero. The near miss demonstrated that the margin between extreme agility and immediate catastrophe was razor-thin. For a relaxed stability fighter, ultra-fast control loops and absolute computer redundancy were no longer theoretical engineering choices. They were the primary conditions of survival. The design decisions of the 1970s produced the most numerous fixed-wing combat aircraft in the world. Global production exceeds 4,600 airframes, with over 2,500 remaining in active service across 25 air forces. Manufacturing remains active, with the modern Block 70 variant commanding a backlog of more than 100 new aircraft in the delivery pipeline. The platform continues to secure skies in high-intensity conflicts. In December 2024, a Ukrainian F-16 pilot successfully intercepted and shot down 6 Russian cruise missiles during a single engagement. 5 decades after its initial design, the fighter remains a primary tool of global air power. The fly-by-wire architecture of the F-16 became the baseline for subsequent combat aircraft. This control lineage descended directly into the F-117 Nighthawk, the F-22 Raptor, and the F-35 Lightning, as well as European platforms like the Eurofighter Typhoon, the Dassault Rafale, and the Saab Gripen. In 1984, the technology expanded into commercial aviation. The Airbus A320 became the first fly-by-wire passenger airliner, carrying the same envelope protection principles into civil transport to prevent pilots from exceeding safe physical limits. The choice to master instability redefined how both military and civilian aircraft fly. The F-16 is projected to remain in production into the 2030s and in American military service into the 2040s. Longevity exists because relaxed static stability, paired with digital flight control, is now the default design philosophy for modern combat aircraft and commercial airliners alike. The core engineering rule has changed. Deliberately reducing a vehicle's inherent aerodynamic stability is the most effective way to unlock performance, provided the platform is controlled by computer systems fast enough and redundant enough to manage the resulting physical complexity. Today, aerodynamic instability is the baseline of modern flight. As aviation enters the era of autonomous combat, we rely entirely on software to prevent catastrophe. We permanently traded physical stability for raw performance. There is no turning back. Share your thoughts on this engineering legacy in the comments.